Basic electricity and electronics. Alternating current. Number 4, oscilloscopes, measuring voltage and frequency. In Part 3, you became familiar with the basic operation of an oscilloscope. In addition to viewing waveforms, the oscilloscope can be used to accurately measure voltages. Let's see how.
The graticule is used to measure voltage and frequency. It's divided into 8 major divisions vertically and 10 major divisions horizontally. Each division is further broken down into 5 subdivisions. Before measuring any voltages, position a trace on the center or baseline. Adjust the channel 1 vertical position control until the horizontal trace is directly over the baseline. To view the first waveform, set the channel 1 volts per division selector to 1 volt and the A seconds per division selector to 2 milliseconds. Again, you will use an audio generator as your AC source. Set the multiplier to the ×1 position and the indicator at 60 Hertz. Adjust the fine or amplitude control to display a waveform 6 divisions in height on the graticule.
Let's measure the peak voltage of this waveform. The peak voltage is the maximum voltage from the baseline to the positive or negative peak. For example, the peak voltage for this waveform is equal to 3 divisions. Remember that each division is calibrated to equal 1 volt. Therefore, to find the peak voltage, simply multiply 3 divisions by 1 volt. This gives a peak voltage or value of 3 volts. Peak-to-peak voltage is the voltage difference between a positive peak and a negative peak. For example, the peak-to-peak voltage for this waveform is equal to 6 divisions. Remember that each division equals 1 volt.
To find peak-to-peak voltage, simply multiply 6 divisions by 1 volt. This gives a peak-to-peak voltage or value of 6 volts. Let's compare these measurements with those of a multimeter. Connect the multimeter across the same 1000 ohm resistor. Then set the multimeter to the VAC setting to show an AC voltage. The meter reads 2.120 or 2.12 volts. The reading on the meter is different from that of the oscilloscope because it is measuring the effective voltage, or RMS, of the waveform. To find the RMS voltage, multiply 0.707 times the peak voltage. This gives you 0.707 times 3 volts, which equals 2.12 volts.
By reading an AC voltmeter, it is possible to calculate the peak voltage from an RMS voltage. To do this, multiply 1 over 0.707 times the RMS voltage, or 1.41 times the RMS voltage. In this example, 1.41 times 3 volts equals 4.24 volts. Let's check this procedure by adjusting the audio generator to read 2.5 volts on the AC voltmeter and verifying the answer against the oscilloscope waveform. It should give a peak voltage of 2.5 volts times 1.41, or 3.5 volts. Checking the waveform, there is a peak at 3 1/2 divisions. 3.5 divisions times 1 volt per division equals 3.5 volts. You can also find the peak-to-peak voltage from the RMS voltage by reading the AC voltmeter. Since the peak-to-peak voltage is twice that of the peak voltage, multiply the RMS voltage by 2 times 1.41, or 2.82. If the RMS voltage is 2.5 volts, you can calculate the peak-to-peak voltage by multiplying 2.5 volts by 2.82, When rounded off, this equals 7 volts. The answer of 7 volts agrees with the waveform.
You can also find the RMS voltage from the peak-to-peak voltage by dividing the peak-to-peak voltage by 2.82. If the peak-to-peak voltage is 7 volts, the RMS value equals 7 volts divided by 2.82. The result is 2.5 volts. This checks with the reading on the AC voltmeter. Now that you know how to use an oscilloscope to measure voltage, let's see how it can be used to measure the relationship between time and voltage of AC waveforms. The period of an AC waveform, abbreviated T, is the time between two peaks. In this example, you can measure the period of the AC waveform by counting the number of divisions between peaks. There are approximately 8.3 divisions between peaks.
The period of a waveform can be found by multiplying the number of divisions by the seconds per division. Using our previous example, this is equal to 8.3 divisions times 2 milliseconds, giving you a period of 16.6 milliseconds. This means that it takes 16.6 milliseconds for a peak to occur after the previous one. You can calculate the frequency or cycles per second by dividing 1 by the period. In our example, you can find the frequency by dividing 1 by 16.6 milliseconds. The frequency is 60 hertz. Remember, 60 hertz was the setting of the audio generator. Now, let's analyze this waveform. Since the settings on this oscilloscope are 0.5 volts per division vertically and 0.5 milliseconds per division horizontally, the peak value is 2 divisions times 0.5 volts per division, or 1 volt. The peak-to-peak value is 2 times the peak value, or 4 divisions times 0.5 volts per division, or 2 volts. The RMS value is 1 volt peak times 0.707, or 0.707 volts. The period equals 6.6 divisions times 0.5 milliseconds per division, or 3.33 milliseconds. The frequency equals 1 divided by the period of 3.33 milliseconds, or 300 hertz.
Now, let's change the settings to 2 volts per division vertically and 50 microseconds per division horizontally. What is the peak voltage of this waveform? The answer is 6 volts. Remember, peak voltage is found by measuring the number of divisions from the baseline in either a positive or negative direction, multiplied by the number of volts per division. This is 3 divisions times 2 volts per division, or 6 volts peak. Now, find the peak-to-peak and RMS voltages of this waveform. The peak-to-peak voltage is 2 times the peak voltage. In this example, it's 12 volts peak-to-peak. Remember, the RMS voltage is found by multiplying the peak voltage by 0.707. Therefore, the RMS voltage is 6 volts peak times 0.707, or 4.24 volts.
Now try to find the period and frequency of this waveform. Remember that the period, represented as T, is the time between two peaks. It is found by multiplying the number of divisions by seconds per division. In this example, there are 4 divisions between the 2 peaks, and the oscilloscope is set to 50 microseconds per division. The period of this waveform is 200 microseconds. Frequency is found by dividing 1 by the time of the period. Therefore, the frequency equals 1 divided by the period of 200 microseconds, which equals 5 kilohertz. In Part 5, you will learn how to use Lissajous patterns to determine the frequency and phase of AC waveforms.